All right, so for this video, we're going to be discussing continuity and tangents and secant lines. So we're first going to start off with what continuity is and what continuity means. And it kind of is self-explanatory. So continuity just means that something is continuous or that it continues, right? So if I have maybe a function that looks like this, and I'm looking at this point here, is this function continuous at this point? Well, absolutely. This point exists. The function passes through it, and it just kind of goes smoothly through. So it just continues through that point. So this function at this point is continuous. But say I have a function like this, and I've got that little gap there. And remember that a hole like this means that there is no value there. The function does not have value. It's undefined. So in that case, at this point x, the function is discontinuous. We call that a discontinuity. This particular discontinuity might be considered a hole, which I'll get a little bit more into. But even though it has a limit and it approaches from this point, because there is no value here, we call it's not continuous. It is discontinuous. And we have three main types of discontinuities, actually. So one main type of discontinuities is an asymptote. So obviously at this x value, there's an asymptote, and this is a discontinuity. Obviously, the function does not continue through this point. Another one was what I just showed you, which we would consider a hole. And then we have another big one where we have graphs like this, where we call this a jump. So at this point, there is a value, but it jumps from one line to another, kind of. And so you'll see that typically with piecewise functions, you might have jump, which is a discontinuity, and at this point we would consider this non-differentiable, which means, first of all, the limit doesn't exist, but it also means that we cannot take the derivative there. I know we haven't really gotten into derivatives yet, but at any discontinuity like this, there is no derivative. They are non-differentiable. All right. So let me give you a few examples really quick. So obviously with that asymptote, that's an asymptote. But if I had a hole, maybe I have a function that looks like this. Maybe I have, let's say, an x squared minus 36 over x plus 6. This function is going to have a hole whenever x equals negative 6. It's going to have that discontinuity. So if I give this some lines, I don't actually know what this function looks like. Oh, yes, I do. I believe so. So give me 1 second. So it's going to be probably down there, and then just kind of like that all the way up, I believe. Oh, I should really double check that. 1 second. Oh shoot, I went the wrong way. Whoops, I was not thinking. Oh, no wait, I don't have to erase that. Oh, well, I guess. Okay, it's lagging a little, sorry. So we're gonna retry that. Let me give myself some better graph to work with here. Okay, so it's gonna be 1, 2, 3, 4, 6. So it's gonna start there, and it's just gonna be this linear line. Da, da, da. And it's just gonna look like that, except when when x equals negative 6, we have a hole here. So there is no value at this particular point. They have a discontinuity because of this in our denominator. Obviously, we can't have a 0 in the denominator. But any of the points around it just continue on. And so the thing that we like to do is we recognize that this x equals -6 is outside of our domain. But when we want to really work with this, we're just going to factor that out. So I know that that turns into this up there. And so then I cancel those out. And now I'm just working with an x minus 6, which is why this is a linear function here, because this is the graph. So all that this tells us is that this is our function, and it happens to have a discontinuity at this point. So that's a good example of our whole. And then, like I said previously, our jumps are typically characterized by a piecewise function. So that's all that continuity is, and that's all of our 3 discontinuities. That's all they are. It's not a complicated concept. Obviously, it's quite literally just if the function continues through that point, it is continuous. And if not, there's a discontinuity of some kind. Now, on the note of our tangent lines, some people are a bit confused as to what tangent means. And so, obviously, it has its own English definition. But let's think about it in terms of our geometry. We used to have tangent lines with circles, obviously. And that's going to be where it touches at this one single point and then just keeps going. It never comes back in contact with this circle ever. And we do the same thing when we have our, what? Why did it do that? When we have our graphs. So maybe I have this graph here, and I want to find the line tangent to this function at this point. That's going to look something like this. And it's not going to come in contact with this function at all for many, many points over, right? So in this immediate area, it is directly tangent to this particular point. A tangent line at this point would look something like that, and so on, right? So that's all that a tangent line is. It's just the line that we form there. And the way that we find that is we first, I'll just redraw that. So if I want to figure out my equation for this tangent line here, I'm going to figure out what the slope is, the instantaneous change at this particular point is. And we can do that by either finding the derivative of a function or using our rule of the slope at a particular point of a function can be found like so. So in that case, we find our slope, and then we have this point, say it's a comma b, right? So we're going to find our slope, which we'll call m, and then I can either plug that into a point slope form, which is going to look like this. I'm sorry that it's all variables. So it could look like this, or I could do my y equals mx plus b. In this case, we're going to use a c because we've already got a b and we don't want to do that. In which case we plug in our y value, we plug in our slope value, we plug in our x value, and then we just have to solve for c, right? And so that's how we would find the equation of our tangent line. But let's say that we have a function. So we've got an example that's not all variables, because I'm sure that was a little hard to read. So let's say we've got this function. Let's say it's an x squared minus 4. That's our function that we're working with. So we can go ahead and find our slope. I know immediately because I know the derivative tricks. I know that my slope is just going to be a 2x, and then I'm going to plug in this point to figure out what it is at this exact point. So let's say that this point is a -1, 3. That's our point. That's our a comma b. So my x will be a -1, which means my slope is -2. Right, and we can always find that with our formula over here, which is what I recommend you use right now because we are not on derivatives just yet. I'm just rewriting that formula. Hold on. So in this case, x approaches -1, So f of x minus f of negative 1 over x minus negative 1 or plus 1. And we're going to keep going. So x approaches negative 1 of our f of x is an x squared minus 4 minus, and if I plug in a negative 1 to here, I'm going to get a negative 1 squared, which is just 1 minus 4. So it's minus a negative 3 or just plus 3 over x plus 1. And then we just combine like terms. So x squared minus 1 over x plus 1. And then we've got a perfect difference of squares up here. So I'm going to factor that out. So it's x plus 1, x minus 1 over x plus 1. These cancel. So now it's just the limit as x approaches negative 1 of x minus 1. If I plug in that negative 1, that gets me a limit of negative 2, or a slope of negative 2, which is what I got up here. And so in this case, our slope, our m, is negative 2. Now, I could take my point, and I could use my point-slope equation. I could do y minus my y value equals my slope times x minus my x value. And there, I've got an equation for a tangent line. But typically, we'll want to put this in slope-intercept form like this. So I'll say that that's a y equals negative 2x plus b. And now we need to figure out what our b is, right? Because we need to figure out our y-intercept for this line, where that's going to come in contact there. So we're just going to plug in those values to figure out our b. It's that simple. So we get 3 equals a negative 2 times negative 1 is 2 plus b. So b equals 1. Our tangent line equation is going to be a negative 2x plus 1. So we've got this equation or this equation. And remember, they're the exact same thing. They're just different ways of writing the same equation for the same line. And that's just the equation for this tangent line here. I'm going to go ahead and clear that. And now we're going to talk about what a secant line is. I'm not sure if we've heard this yet, but a secant line is very similar to a tangent line. I would go so far as to say that it's easier to deal with than a tangent line, because what a secant line is say I've got this function, right? And I want my secant line between these 2 points. I'm quite literally just making that line. So they're going to give me these points, say a comma b and c comma d. So let's say the points they give us, we want to find the secant line of, let's give ourselves the same function as before. We'll do an x squared minus 4, I believe it was. So we want the secant line of this function from points, let's say negative 2 comma negative 1 and 1 comma 1. We'll say these are the points they gave us. All we have to do here is make sure that we get the slope, which we do with our normal slope equation, which is just like from algebra, because we're given 2 points. So that's going to be, in this case, it's going to be a 1 minus negative 1, which is 2, 1 minus negative 2, which is 3. So our slope in this case is a 2/3. And now we just need to find our y-intercept, right? So this is going to be, I could go ahead and write my point slope equation right now. I can just choose one of these points that I like. So I could do y minus y1, so I'll do that, equals my slope times x minus negative 2. So there we go. I've got an equation for my secant line. But again, we typically want to do it in slope-intercept form. So I've got a y equals 2/3 x plus b. And I'm going to just pick one of these points. You can plug in either one. You should get the same value for your b when you do this. And I'm going to plug in this one right here. So I'm going to say negative 1, right, because it's my y value, equals 2/3 times my x value plus b. So negative 1 equals negative 4/3 plus b. add 4/3 to each side. So I get 1/3 equals b, which means that my slope-intercept equation is this. And again, this is all that they're looking for when you're being asked to find the equation of a secant line. And what I showed you previously was all that they want when asking for the equation of a tangent line. I know it's a pretty confusing concept, and it doesn't feel like there's really many like real life applications. But honestly, I feel like they're not too intimidating, I hope. On that note, this is all that we were going over for this video, so this is all done. Thank you for watching.